So here's an example where we want to rotate an object to get a volume. The object we're rotating is the region bounded by y equals 4x minus x squared and y equals 3. So first let's graph that. If you factor this, you get x times 4 minus x. So it has intercepts at 0 and 4. So at 0 and at 4. And it's a parabola, it opens down because its leading coefficient is negative. So you get this shape. And the line y equals 3, so we'll draw it here. Now we know it's about there because I looked ahead of time. If you want to try to find where they intersect, because we want to only rotate the region bounded by them, and that'll be this region in here, in the inside, we want to check their intercepts. So you set 4x minus x squared equal to 3. You bring everything over to the right and you get 0 equals x squared minus 4x plus 3. So 0 equals x minus 3 times x minus 1. So they must intersect at 1 and at 3. So we have our two x-intercepts for the function, the x-coordinates of the intercepts. And we're asked to rotate around the axis x equals 1. Sorry for the typo over here. We want the axis x equals 1. So we draw our line x equals 1. Again, if it says x equals 1, it seems backwards. It sounds like it should be horizontal, but it's vertical. It's every coordinate, or every point with an x-coordinate of 1. So the first thing we do after we've got our region and our axis is draw the mirror image. So we draw our mirror here. And we draw our slices, our representatives. Now I'm doing them parallel because that seems like the easy thing. If I was considering this shape and I wanted to use horizontal slices, I'd notice that every slice touches the same function twice, which is very difficult, so I don't like that. I want my slices to go vertically. And since that is parallel, I want to think shells, which is 2 pi radius height. So that's the formula I'm going to use. We can see our limits of integration, our bounds of integration, by looking where our slices start and where they stop. So v is the integral from 1 to 3. Our formula is 2 pi radius times height, so I usually write that down. But since we're going from 1 to 3, we know that they are x-coordinates, so dx. So now I need a formula for r, the radius, and h, the height. So here's the actual picture I would draw if I was doing this problem from scratch. After I found the region, and I drew the mirror image, I would draw one good cylinder. I'll put it on the far side just to give us an actual cylinder to draw and some actual numbers to talk about. So we're going to integrate this x, which gives us this vertical line, which rotates its mirror images this vertical line, and you connect the top with a circle and the bottom with a circle. So to find the radius of that, I need this distance that goes from the dashed line out to the x. But x is from the y-axis out to the x. So I don't want the entire distance x. I only want this piece on the right. And we know that we're going around the line x equals 1, so this distance is a 1, which means my radius, r, is x minus 1. So I'm going to update my formula. V is the integral from 1 to 3, 2 times pi times x minus 1. What I'm missing still is my height. The height here is given by the height from the axis up to the function minus the height from the axis up to the other function. So I've got two lines there. The big one is the 4x minus x squared, and the small one is the 3. So I just subtract them to find the height in the middle. So times 4x minus x squared minus 3 with respect to x. And that's our entire setup. Okay? So remember, the first order is draw the picture, mark your slices, pick the easiest slices, and that tells you whether you're going to use shells or washers. That's the question we get most often. Just whichever slice is easier. If they're parallel, you're using shells, and if they're perpendicular, you're using washers. Hope that helps.